we present Diffusion-SAFE, a shared autonomy framework with diffusion for safe human-to-robot driving handover. Our work is motivated by common failure cases in autonomous driving, shown on the left, such as crashes and drifting, which often stem from inaccurate trajectory prediction and poor adaptability. On the right, we highlight complex multimodal scenarios like intersections, where multiple valid future paths exist and managing uncertainty becomes critical. These cases underscore three fundamental challenges in shared autonomy. First, the need for long-horizon prediction to enable smooth control handovers. Second, accurately modeling multimodal human intent. Third, supporting real-time, interactive collaboration between human and robot. To address these challenges, we propose a closed-loop shared autonomy framework that ensures adaptive, safe, and seamless transitions between human and autonomous control. Our framework, Diffusion-SAFE, uses two diffusion models to enable safe shared autonomy. The evaluator predicts the human's long-term intent and assigns a risk score based on past behavior and visual input. The copilot generates safe, short-term actions from expert data. If the evaluator detects risky behavior, control smoothly shifts to the copilot using a partial diffusion mechanism. We've validated this approach in both simulation and real-world ROS-based race cars. Here's the architecture we use for action sequence prediction. At the core is a U-net-based noise estimator, used in both the evaluator and copilot. It starts from a noisy action sequence and denoises it over K-steps to output clean steering, throttle, and brake commands. Our U-net uses a downsampling-upsampling structure with residual connections. Inputs include the noisy actions, conditioning information by feature-wise linear modulation, and time embeddings to guide the diffusion process. The encoder extracts features, and the decoder reconstructs the clean action sequence. We now explain how our framework achieves smooth control handover. At the core of our method is partial diffusion, a mechanism that enables gradual transitions from potentially unsafe human to the safe copilot. This process consists of two key steps. First, forward process progressively adds noise to human actions, effectively weakening them. Second, reverse process denoises these actions toward the copilot's safe and optimal policy. This diffusion-based transition is inherently smooth and does not rely on handcrafted blending mechanisms. At inference time, we introduce a controllable parameter, gamma, to modulate the degree of handover. A lower gamma retains more influence from the human driver. A higher gamma shifts control more strongly toward the copilot. It is important to note that the control handover does not always begin with gamma equals 0, as the initial human actions may already be unsafe. Therefore, selecting an appropriate initial value, gamma 0, is crucial to retain some level of human input, while still ensuring a safe and smooth transition to the copilot. To determine an effective gamma 0, we evaluated a range of values using two key metrics. Smoothness, quantified by the variance in vehicle velocity. Unsafe rate, defined as the percentage of runs that resulted in collisions or off-road deviations. By jointly considering these metrics, we found that gamma 0 equals 0.4 achieves the best balance, offering reduced risk while maintaining a smooth and stable transition of control. To showcase the capability of our partial diffusion approach in the handover process, we compared it with a simple blending method. On the left shows the simple blending. In this approach, the blended action is computed as this equation shows, where K gradually decreases, shifting control from the human to the copilot. However, this method often leads to unsafe off-road states during the transition. Notice that when the vehicle drives off-road, the copilot is still able to correct it back on road. On the right shows partial diffusion approach. Instead of direct blending, our method ensures a smooth and safe transition from human actions to expert copilot actions. The handover happens gradually but in a more controlled manner, avoiding abrupt shifts that could lead to instability. This segment highlights key frames from our car racing V0 simulation, demonstrating the transition of control from the human driver to the copilot. From 0 to 2.1 seconds, the human is driving well, maintaining strong performance. At 2.1 seconds, when the score drops below a predefined threshold tau_NLL, the system starts a gradual handover. From 2.1 to 2.5 seconds, the human inputs with the copilot's planner are mixed using partial diffusion approach. By 2.5 seconds, the transition is complete. and the copilot fully takes over, generating expert-level trajectories until 4.7 seconds. This highlights how our framework ensures a smooth and controlled shift in autonomy, balancing human input with safe, expert actions. Here, we have 4 demo sequences showing smooth and successful handovers in the simulation. These clips highlight how our approach makes the transition adaptive, safe, and seamless, keeping performance stable even when the human driver starts to struggle. We conducted an ablation study in both simulation and real-world settings to assess each component's impact. For the evaluator, visual context, position, horizon lengths, and past human actions all proved essential to performance. We also compared our diffusion-based models with 2 multimodal baselines, LSTM, GMM, and BET, both of which require preset modes. As shown in the right tables, our approach outperforms them in accuracy, safety, and efficiency. We validated our framework on a real-world ROS-based race car. Instead of using a mounted camera, we simulated the top-down view by tracking the car's pose via motion capture and aligning it with the static overhead image using April tags and homography. A Cropper ROS node extracts 60 × 60 image patches in real time, which are used to train an autoencoder for visual context to sync pose and joystick data running at different rates. We build a synchronizer node. All state, control, and image data are logged in ZAR format for fast access. We collected demonstrations from multiple drivers across 15 tracks to ensure dataset diversity. We present 4 real-world demos showcasing smooth and successful handovers under varying start points, driver strategies, and handover timings on unseen tracks. These demos showed that our framework can smoothly and adaptively take over control when needed, ensuring safety and keeping performance stable even as the human driver starts to lose control.